Yes. Good. In this presentation, I will try to explain the CRYSTAL-Kyber structure, which is one of the finalist candidates in the NIST round 3 standardization process. In this presentation, we have a brief introduction, and then we introduce some fundamental lattice-based cryptography. Then we introduce the Kyber specification and Kyber encapsulation mechanism. Kyber encapsulation mechanism. Then we review some performance results in different platforms, and then we have search attacks and an example in the Sage. All of you aware about the importance of the public key, so we can skip these materials and the different approach for post-quantum cryptography. So for the NIST round 3, as you know, we have some candidates in the finalist and alternative. There are 3 lattice-based cryptography in the finalist, Kyber, Saber, and Entro. And at the same time, we have a FordoCam and Entro Prime in the alternative candidates. In this between them, CRYSTAL-Kyber has a small key size and can be implemented efficiently on different platforms. So it has a good chance to be standardized. Furthermore, it has a same platform with the CRYSTAL-Dilithium, which is one of the finalists in the digital signatures scheme. So we need to study more details about this structure. All lattice-based cryptographies crypto system are based on 2 main categories. The learning with errors as one of the main problem. Is one of the main problem, and lattice-based and Kyber is based on this approach. As you know, given matrix A and T, you can easily find the matrix S by inversion the matrix A and the multiplication it by T. But if we add some error with a small coefficient with this equation, finding S given this blue matrix is very hard and can be considered and can be considered as a problem for building a post-quantum crypto system. Here we have an example that you can see that adding this error can be changed the result of this equation. So the finding the green matrix here can be considered as a hard problem. The second problem for providing the post-quantum crypto system based on the lattice-based is short integer solution. In this problem, finding the x such that ax equal to 0 with a small coefficient of x can be considered as a hard problem. I mean a small coefficient of x which can be equal to 0, 1, or -1. Kyber, as I said, is based on the LWE, so we focus on this scheme. In this scheme, Alice in the key generation choose some random number as A and choose S and E with a small coefficient. Then she computes this equation to compute the T, matrix T. A and T can be considered as a Alice public key. So Bob used his own own random number, and using the Alice public key, he compute this equation plus some a small error and the message. So he can compute the ciphertext of the U and V. We want to rearrange this equation to find how he compute the U and V, and what is the relation between these ciphertexts with the Alice parameters. As we see, V is computed by RT plus E2 plus M, and T can be actually rewrite as a AS plus E. So if we ignore the multiplication between these yellow matrices with small actually noises, we can actually rewrite the V as a RAS plus M plus a small value here, small noises, I mean. And U again can be computed by RA plus E1. And again, if we actually ignore the multiplication with error and show it only with actually small noises, we can rewrite this equation by RAS plus actually a small value, which is close to the V minus M. Alice can be used of this equation to decrypt the message M. So she actually compute V minus US to actually compute M plus a small value. So she can actually recover the message M using the given ciphertext of U and V. Any questions so far? Okay. So if you consider the dimension of the A and S matrices here, if A, suppose A has n by n actually elements and S has a columns, we can see that U has a n elements and V has actually power of 2 elements. So for encrypting the two elements here, we need actually n elements for as a actually extension. So the main problem in the lattice-based cryptography crypto system is the size of the public key, which is actually huge. As we see, we need n over k actual elements per each encrypting per bit. So for solving this actually problem, some actually methods for building the structure matrix have been proposed. For example, ring WE over this actually ring needs only one row of elements to actually building the whole A matrices. For example, the second row can be computed by if you consider this actually values as a coefficient of the polynomials. We need only the multiplication between x and the first row, such as you can see here, and reduce it respect to this ring to compute the second row coefficients. The second actually problem of the lattice-based cryptography is a huge number of the arithmetic. As you know, we actually for computing between two vectors with n elements, we need to n power of 2 actual multiplication. So for solving for more optimization, the entity actually function can be used here, which reduce it to n log n actually number of n log n multiplication. If we n is equal to 256, the entity can save almost 97% of the multiplication, which is very significant actually optimization. LWE and LWR has actually are very similar to each other. In LWE, the noise actually added from the Gaussian error, and in the LWR, the noise actually comes from the rounding of the rounding the values to the smaller interval. So both actually the structure matrix approach can be applied on both of these actually categories, and therefore we have 4 different approach for providing the post-quantum crypto system. As you know, the New Hope is based on the ring LWE, Kyber is based on the module LWE, Round 5 is based on the ring LWR, and Saber is based on the mode LWR. And Kyber and Saber are in the actually finalist in the round 3. Here we have a comparison between different, actually between selected lattice-based scheme in the round 3. As you see, Kyber and Saber is based on the module learning with error and rounding respectively, but FurtherChem uses the pure learning with error. Therefore, the key size here in the FurtherChem is actually significantly bigger than actually other streams. N2 is based on the shortest vector problem. The polynomial rings in the Kyber and Saber is the same, and n here is the power of 2 in both of this approach. However, Kyber used actually the prime q for reduction in different stages, and Saber used the power of 2. Therefore, implementing the Saber can be actually the Saber actually can be implemented more efficiently. For computing choosing actually S and E in the encryption or generation of the KEM approach, we need actually the sampling. We need actually a sampler. The Kyber and Saber use the centered binomial distribution in the sampling actually approach, and N3 use the uniform distribution, and for the claim use the Gaussian distribution. Here we see actually different parameter set for the Kyber for different security levels. For all these actually security levels, n is equal to 256. And as you see, by increasing the k here, the security will be increased. I should mention that the value of q has been changed in the actually recently in the November. So these parameter sets actually are known as a Kyber version 2. Here we have actually comparison between Kyber and Saber in different category levels, security levels. As you see, all Saber has actually a smaller key size compared to the Kyber. For example, for the security level 1, we have actually 1632 bytes for Kyber secret key for Kyber, and 800 bytes for actually public key. And Saber has actually a smaller key size. And we can actually compare the security between these schemes. Although NIST actually recommend that use of 143, 207, and 2 actually 72 bits security for category 1, 3, and 5 respectively. Both of this scheme has actually a lower security in classical and quantum security respect to compared to actually NIST recommendation. And as you see that Kyber has actually provide a smaller, actually lower security compared to the Saber for all these categories. So it can be, this is one of the actually weakness of the Kyber compared to other candidates in the finalists. Here we have actually we showed the 3 main fundamental actually function in the actual public encryption. Alice, as I said, use the actually seed for sampling A. We suppose that the actually A elements are in the entity actual domain here. So he chose actually chose the CBD or centered binomial distribution for E and S. Then she should actually convert them to the entity domain and computes actually this equation to actually compute T as a public as a her public key. Bob on the other side extract the T from the public key and actually again choose A transpose using the seed and actually sampled R, E1, and E2 using the CBD and his own random number. Then he actually convert R to the entity domain and compute the A transpose modification with R, and he needs actually a back transformation from entity and adding the noise to the to compute the cybertext of the U. we have actually the same equation here for computing V plus actually the decompress of the message. So he actually compute both this actually cybertext and send it for the can be used for the decryption on the other side. And Alice used this equation to compute the recovery of the message M as a shared secret key. And as you know, there are some actually papers that shows that the public key encryption, the security of the public key encryption can be broken in the lattice-based scheme, and Kyber, such as other actually lattice-based scheme, use the FO transform to provide the key encapsulation mechanism, which is more secure than the PKE. Now we review some actually performance results for different platforms. In the for CPU implementation, the submitter team actually reports these numbers for one core of the actually Intel Core i7, and the reference code number can be optimized using actually the advanced vector extension, which is actually reported here for different categories. For ARM Cortex M4, as you see, we have actually this number from the reference one, which is recently published and reports the optimized number. For example, for the security level 1, for key generation, we need almost actually 450 kilocycles. And for encryption, encapsulation and decapsulation, we need actually 586 and 543 kilocycles, respectively. And reference to actually reports all these numbers for different function. As you see, the most time-consuming part of the Kyber is the catch-up. It needs almost 70% of 70% of all actually clock cycles. And for the FPGA implementation, we have actually this reference which use the RISC-V actually core. As you see, the required clock cycle here is more than actually the Cortex M4 because of using this core, and therefore this paper can't use the actually the main advantage of the FPGA to actually full pipelining. Again, you can see actually the resource utilization. This approach uses the 5 DSPs using the actually almost 2K LUTs and works in the 60 megahertz. Again, actually, we can see that the most actually time-consuming parts of the design is to catch up, and as you see, without excluding the hash function, actually we have a 30%, 15%, and 23% of the actually required clock cycles for key generation, encapsulation, and calculation, respectively, in the secret level 1. Here we have actually comparison between different actually schemes in the category level 3. As you see, Kyber here use the actually software hardware design, and the number for generation, encapsulation, decapsulation are in the order of the millisecond. However, FrodoCam actually needs almost 45 milliseconds because of actually due to the huge actual key size. And Saber in the hardware software design has the same actually almost performance, but the last one actually just published recently used actually the instruction set architecture and can actually improve significantly the actually performance. It needs only 21 actually microsecond for key generation, 26 microsecond, and 32 actually microsecond for encapsulation and calculation in actually this frequency. I should mention that the Kyber here used the old parameter, which is can be considered as a Kyber version 1. And again, you can see that for the CAM needs actually more memory and more actually computing, arithmetic computing. For side channel attack, we should consider the actually timing attack. As you know, that actually Kyber doesn't have any secret defense branch, so it can be actually implemented secretly. But designers should be considered actually using the constant time modular reduction to avoid timing leakage in this actually part. For differential attacks, actually, if we want to use actually the long-term keys, we need to use some actually methods such as massive implementation, which is actually proposed in reference 1. However, it needs actually the overhead of actually factor of 5.5 in the actual decryption. And for actually template attack, we need to actually use the constant runtime and controlled flow to avoid these types of attack. And for more detail, we can actually read this mentioned here. Now, actually, I provide a Sage example. If you don't have any question, we can actually run it together and see the result. Any question?
So Mojtaba, at the end, you ask some questions here, everybody is following. Seems nobody has questions.
In the actually, I provide actually the version, the Kyber 5.12, which is the security level 1. In this actually scheme, the K is equal to 2. In this actually scheme for key generation, we need actually the initial seed. The initial seed has a 256 bits, as you see here. So with performing the actually key generation or key pair actually function, we have A with the Alice actually choose A, S, and E. A, as you see here, has a dimension of the 2 by 2 vectors, and each vectors has a 256 actually elements. We suppose that these elements are in the entity domain. Then she computes actually the S and E, as you see, with a very small coefficient. The coefficient are between -2 and 2, and then she should actually convert them to the entity domain, as you see here. I should mention that the dimension of the S is a 2 vector of 256 actually elements. E has the same actual dimension. Then actually using the key generation function, she can compute the public key, which has actually 800 bytes, and secret key, which has actually 1,600 actually bytes. In encapsulation, actually, which is performed by Bob, he used again actually encryption seed, random number, then using actually FO transform, as I said, he actually used he actually computes the actually the coin some random number here and the message. Using actually the public key, some the message, and actually some random the random number, he can compute actually the encryption and computing the ciphertexts. as you see, the message here has 256 elements, and each element actually all elements are only 0 or q minus 1 over 2, which is actually this value, as you see. And he compute a transpose with the same actually dimension 2 by 2 by 256 elements, as you see here in entity domain, and again the random number R with a small coefficient, and two actually random number noises, one of them E1 with two actual vectors of 256 elements, and the second one has a one vectors with actually only 256 elements. So he computes the cybertext with 736 actually bytes. And again, using the FO transform, he computes the shared secret key, which is 32 bytes. They are actually shared secret key used the shake 256 and SHA-3 256 providing actually computing the shared secret key. Bob used these two catch-up function. And for the decapsulation, Alice used this given cybertext and her own actually secret key to recover the message, and actually the random number that Bob uses. So she computes the V minus US, as I said in our previous slides, and as you see, then she actually convert these elements to 0 or 1665. If this value is close to the 0, for example, the first one is converted to 0, and the second one is converted to the 1665. As you see, the converted message is similar to actually a message that Bob has been used. Then, given actually this by recovery of this message, she can actually compute the shared secret key. I said actually the message and the random number that she recovered using the decapsulation mechanism will be actually used again for encryption to actually verification. And in the verification, in the encryption, again, we have these matrices, as you see. And again, at the end, Alice can compute her own shared secret, which is equal to the secret key of the Bob. Thank you. That's it. If you have any question, I can actually answer if I can.
So thank you, Moshaba, for the presentation. Can you explain the degree of polynomials? And you go back to slides for key size, ciphertext size, and security levels. Could you explain those to us?
Yes, actually, here actually the secret key for the for example, the category level 1, Alice used actually the matrix A here has a dimension of 2 by 2 by actually 256 elements. After actually all her computations, she can actually compute two vectors of actually numbers. Each of them has a actually 256 bytes. She actually concatenate them with each other and actually add some actually other numbers with actually catch-up transform and compute actually the public key size of 800 actually bytes here. Again, she actually compute her own actually secret number which concatenated with the public key and her own seed number to provide secret key. So, for example, secret key here is actually concatenation of her secret key, her public key, and the seed that he used for actually providing the matrix A, which is actually 1632 bytes, as you see here. And for the cybertext, actually, as I actually show you in our first slides, the dimension of the U and V is actually N and K and N plus K, and actually she has actually two vectors of these actually elements, which provides 736 bytes of the cybertexts. All actually for this category, all matrices has two actually vectors, at least two vectors. For category, for example, level 3, it has actually three vectors, and for category level 5, it has a 4 actual vectors. As you see in the as you see for K here, we have actually the number of vectors for S and actually cybertexts in the Alice and Bob computation. So by adding the for increasing the security, we need only increase the dimension of the secret key and A for all the actually computation. You can see here that, for example, S in the category level 1 for Kyber has it actually has a 2 column, and A here has a dimension of 2 by 2 by actually 2 by 2 vectors. So for each she computes two actually vectors of T, each of them using actually 2 vectors of A and 1 vectors of S, plus actually 1 vectors of E. In the category level 3, we have actually 3 columns for S, 3 columns for E, 3 columns for T, and the A has actually 3 by 3 vectors. So for computing the each actual vectors of T, she should compute actually 3 actually vectors of the A using the 1 vectors of S and 1 vectors of E to compute 1 vectors of T. And she actually repeat this actually equation for all of these actually repeat this routine 3 times for category level 3. For category level 5, she should actually repeat this equation 4 times. I can actually show you the details of the, for example, computation, the key generation that we use. The secret key here has actually for the category level 1 with k equal to 2. Shared secret key has a dimension of 2 vectors of 256 actually coefficients, and it has actually the same coefficients for here we compute actually a multiplied by s, which is actually secret key. And as you see, for the Kyber k, we should actually repeat this equation to compute all vectors in the public key. And then we add actually error to this, to all these actually vectors in the public key. That's it.
Moshtaba, what is decryption failure? Where is it coming from?
Decryption failure. I have actually some numbers here for actually failure. I don't focus on this value, but in the decapsulation, when actually Alice compute the message and actually a random number of the bobs, he again actually compute the, just a second, she again actually compute the cybertext and verify that the given cybertext is equal to the actual computed cybertext or not. If actually the given cybertext is equal to the actual computed cybertext, she can compute actually the shared secret key correctly. But if she can't actually compute it and the fail is equal to actually 1 here, so it's actually I don't check it, but I guess it. I will check it. I am not sure. I should check it in more detail.
I think it has to do with the error message when she decrypts the like finding the error message and everything. It could be off a little bit here and there, and so each bit could be off.
Yes, I guess it's
so
actually
it accumulates over, like the likelihood of each bit is very small, but in total, then you get a possible error. But yeah, I'm not 100% sure either. But it has something to do with the adding the error and then trying to undo the error.
Oh, okay. I should check it actually in the decapsulation mechanism.
Very nice.
Hey.
Thank you so much.
Thank you.
I have only one question, very small one. So you said that Kyber has like bigger key sizes and also provides less security level, like less security, so than Saber. So what is the advantage of Kyber in comparison to?
Actually, in comparison with the other, for example, with N-through, it can be implemented efficiently, more efficient on the different platform, and actually, in comparison with Saber, I guess the main advantage here is actually the same platform for the lithium, which is another actually signature finalist here. So if you consider them as actually package, the system needs only actually one actually scheme to provide the both actually key encapsulation and digital signature actually a scheme for post-quantum cryptography, which is very actually I guess important actually advantages here.
I don't think it's actually the same algorithm. I don't know that they have too much in common, but I know they're made by the same people and stuff, but I don't know how much overlap they have, but maybe some, yeah.
On the other hand, actually, most of people in the other things actually, or actually cryptographer claim actually about the security of the Kyber and actually says that it's not secure compared to other actually schemes. So yes, it's it has some disadvantages and has some actually advantages.
Okay, thank you so much.
You're welcome. Yes, the all actually lattice spaces for example, Kyber, Saber, Nuco, and ROM5 has the same actually algorithm. It's very actually similar concept for all of them. You can actually change one of them to another with some modifications in the actually I guess the time is limit. Yes, sure.
Yeah, I feel like the one they choose between those three is just going to come down to which one has more support in the end, like which one has more companies like Microsoft or Amazon trying to implement it or something.
Excuse me, pardon me, please. I don't follow you.
Oh, I was just saying between like Kyber and Saber and Intru, like I get the feeling like unless they find some bigger issues with one of them, the one they choose is just going to be the one that has like more momentum behind it, has more companies picking it and wanting to test it and stuff.
Mm.
Like I don't think they'll say, oh, this one is a slightly smaller key, so we're going to choose it, or this one's slightly faster. I think they'll say this one has more effort behind it and more focus or something. So that's my opinion. I don't know.
Yes, you're right. Yes.
Also, another question. Probably I missed it. I'm so sorry. Is it based on structured or unstructured lattices?
No, it's actually used a structure. Yes.
Mm-hmm.
It used the modulo LWE.
Okay. Mm-hmm.
Yes, you have actually some matrices that the block in the ring LWE, you has a row, and you actually can build A with all rows. But in the modulo, you have actually some blockers, and the blocks actually can be actually repeated.
Mm-hmm. Is that the main difference between structured and unstructured lattices?
No, I mean actually both ring and modulo is structured. For the ring, we use only one row. For the modulo, we use actually some blockers.
What is the difference? I'm sorry. I'm sorry for asking so many questions. If you don't.
That's okay. I'll show you on my previous slide here. I said that if we use actually the unstructured matrix, which for example before the CAM uses this scheme, we need actually store all actually rows, all elements, and actually we compute the arithmetic for all of them. However, when we use actually the structured matrix, for example, for ring LW, we need only actually store and use with one row, and other rows can be computed actually with multiplication of the first, for example, row with x to compute the second row, and actually continue for other actually rows. This is actually the structure of the ring LWE. For the modular LWE, you have a block, not actually the row. You have, for example, a block here, and you repeat this block for all actually for building the whole A.
Mm-hmm. Okay, thank you so much.
You're welcome. There are references. There is a reference, which is the worst case to average case. The title of the paper is the worst case to average case scenario, which actually explain the ring LWE and modular LWE can be used in the actually average case.
Mm-hmm. Okay, thank you.
You're welcome. Any question?
Mushtaba, explain what algorithm is used in for reduction of polynomial, and what's the degree of reduction polynomial?
Okay, actually, for all of actually this scheme, the main actually computation part is the actually modular multiplication, and for the Kyber version 2, we have to actually reduce our elements respect to Q, which is 33229. You can use actually the Montgomery reduction and Barrett reduction in actually our algorithm. For actually in the reference actually implementation which is reported with actually submitter team, they use the fast actually Montgomery reduction, and they actually recovered the number from the Montgomery domain at the end of the actually this multiplication. I mean, the element actually goes to the Montgomery domain with, when we actually compute the A, and when we actually sample the convert the E and S to entity domain, and then we actually have a back transformation here. But we can actually in the other actually implementation that I check in the hardware implementation that I check, most of them use actually the Barrett reduction. Both of them actually has the same actually performance in the hardware actually side, and the most actually important parts for implementing one of these actual algorithm is using them in a constant time actually scheme. We should actually use them to actually to avoid the timing leakage. Another thing here is the rejection actually approach when we use the when we sample matrix A, we need actually reject some samples which is bigger than the actually 12 bits. I mean, is bigger than actually the queue. But in the reference code or in the reference implementation, the CPU implementation, they combine the actually the Montgomery reduction with another actually rejection sampling with each other to actually provide a more efficient algorithm here. However, in the hardware implementation, we can actually choose another actually, you can use actually separate reduction using, for example, the Barrett reduction, and have actually the rejection sampling with separately with, I mean, two completely separate steps. Without any actually decreasing the performance.
Sounds good. Thank you, Moshtaba. Any other questions? Let's see who is here. Brian, Imra, Pakiza, Mila, Brandon. Any questions?
Nothing from my side.
I think I'm good. I probably will look over this a couple more times this week, but thank you so much for the information. It was a lot of good stuff.
I also thank you, Moshtaba,
Thank you.
for this nice presentation.
Thank you.
Hey, thank you, Moshtaba. And can you also please share the slides if possible?
Sure. Thanks.
Thank you.
You're welcome.
Well,
Thank you.
Thank you, Moshtaba.
You're welcome. Thank you, Dr.
Yeah, please send your slides and the link to that Sage link if you could. Thanks.
Okay. You're welcome.
Okay.
Thank you. Thank you all.
Bye, Bye.
Bye. Thanks.